Good day and welcome to the Math Salon. I'm Dr. Anumende. Today we still look at roots of equations, approximations, better approximations. Previously we already saw that you could already know how to determine that a root of a certain equation lies in a certain interval. And the most importantly was to check the function value at the lower interval to the function value at the upper interval, upper bound. And then you compare the signs. If they are opposite in sign, then it means it contains a root. But of course, if I have a root 1, then it means that answer lies between minus 10 and 10, but it also lies between minus 5 and 5, also lies between minus 2 and 2. Each of these are true, but some are better than the others. That's the idea. We try to get a better approximation. So I'll just let us again see a small sketch here. So this is my Cartesian coordinates. I have here my f of x axis and the x axis here, but this is also the y axis, Let's say there's a function like this one. So it is the graph that goes wherever it goes. And it crosses the x-axis. Because it crosses the x-axis, it means it has a true root here. A true root is there. But I don't know it. I don't know. So what I do is I look for a value that is close to it. Let's say A. A is here close to it. I say that is the first approximation. That can happen. Let's say that in this question, you say, given that a root of the equation x to the power 4 plus x cubed plus 3x squared minus 9x minus 2 is equal to 0 lies in this interval. So I've already been given an idea that it lies in the interval 1 to 2. So it means I can make a good guess to start. For example, here they say start 1.5. So let's say my A is the starting one, is the one I want to start with. I know that at the point A, if x is equal to A, then the value of y is f of A. So if x is equal to A, then my y will be equal to f of A. So that means that this point here has coordinate as A, f of A. If I take a tangent of that, it means a line that just touches that curve at that point, only at that point, then I call it a tangent. But you see, that tangent, I can make it also to cross the x-axis, so it's going to cut the x-axis somewhere. So in order to do that, it means that, if I want to write the equation of this line, the tangent line, then we know that normally this will be y minus y1 is equal to m into x minus x1. If I'm given a point x1, y1 like here, so it means I can actually replace that as y minus f of A is equal to m into x minus A, right? That's fine. So to get the equation of a line given a point, you can do that. The only problem is you don't know m. M is a gradient. But I know this function. And to get the gradient of this line at that point is just differentiating the function. So this is my f of x function here. So that means my f at this point, my m at that point is f prime of A. So you differentiate this function. And at this point, then you're going to get the gradient of this graph at that point. So if that is true, then I can replace this with my y f of A is equal to f prime of A x minus A. So this is the equation of this tangent line. Now, I want to look for the value of x at which this tangent cuts this x-axis. That means at that point, the equation of the tangent had y equal to 0. So this tangent cuts at this point when its y is equal to 0. So the tangent cuts x-axis when y is equal to 0. So if I put y equal to 0 here, then I get minus f of A is equal to f prime of A x minus A. I want to make x the subject of this formula. So I can divide this. So this is minus f of A divided by f prime of A is equal to x in minus A. I can take this A to the other side. It becomes plus A. So that means A minus f of A divided by f prime of A is equal to x. See, and the x is the new value that I get. So which means that here, if I know the first guess, A, like 1.5, I can get a new guess by using this formula. So we write x is equal to A minus f of A divided by f prime of a, where this a is the first approximation and this new one will be the second approximation. And you can repeat this again for another approximation. So if that is the case, it means this is what is actually called the Newton-Raphson method approximation. So what do we need? Let's say this function here, f of x, is equal to x to the power 4 plus x to the power 3 plus 3x squared minus 9x minus 12 is equal to 0. Sorry, not equal to 0, necessary. I'm just picking the part of that function. Then I need f of a. In our case here, a is equal to 1.5 or 3 on 2. So I will say this is f of 3 on 2. You can substitute 3 on 2 there with your calculator or so and come out with the answer. I wouldn't bother to do that now. So then we need f prime of x, because we need the f prime here. F prime of x means the derivative of this function, and that is 4x to the power 3 for this. This is plus 3x to the power 2. This is plus 6x. This is minus 9. Then I need the f prime of a, which is f prime of 3 on 2. And that's equal to, you substitute 3 on 2 into this and you get a certain number here. Once that is done, you just come and put here, you get the second approximation. So the second approximation would be x is equal to, you can call it b if you want, whatever you want. A, which is the 1.5, so I will write here 3 divided by 2. It says minus f of a, this is f of 3 on 2, divided by f prime of 3 on 2. This you already have. This 3 on 2 is there. Nothing changes. This f of 3 on 2, you should use this. Take this, put it this, and into your calculator, get a number. You put the number here. You do the same thing here. You put 3 on 2 into this one, you get it, and you feel that you're going to get something that indicates that it's going closer to the root. So you get a new number, and that new one is a better approximation of the 3 on 2. So you get something x, which is better than this. If you call that b, for example, that is 3 on 2 minus f of 3 on 2 all over f prime of 3 on 2, then the next approximation that I can call c would be equal to, you use the one that you already did. This was the beta of the 1.5. I want the beta one of this one. So then I'm going to get beta b here now, because that is the next one. Say this one now was 1.7, for example. So then this is 1.7. After this calculation, you get a number. So if you put that here, then this is going to be minus f of b, f prime of b, which is a new thing that you would have calculated. You would have had another approximation. That's the meaning of doing it twice. You can do it 3 times and 4 times, and each time it gets better until you make this point. So it will jump here, then it's going to jump here, and jump, and gets closer and closer until you hit the point, if you do it real many times to the limit. Okay, I hope you liked it. If not, please leave us a comment for us to do better. And most especially, thumbs up, subscribe, share with your friends. Bye-bye.